PhD student from USC. I'm going to present our paper, FastMask Segment Multiscale Object Candidates in One Shot. And this is a joint work of USC, Fudan University, and Face++. Instant segmentation is a research topic that targets at simultaneously detect object location and infer its corresponding boundary informations. A common approach for this task generally involves two steps. The first one is to propose high-quality object candidates with good recall, and the second step is to perform classification on them. In this work, we focus on the instance proposal as it defines the upper bound performance for a detection framework. Our goal is to develop a faster and more accurate proposal algorithm. For object proposal, a grand challenge is scale variances, because different objects, as well as the same objects, can appear at very different scales in one single image, as you can see in the following two examples. A typical approach to tackle this challenge uses image pyramid, where an image is resized into different scales and input into an object detector repeatedly. However, such procedure involves large redundant computation. To deal with this issue, in this paper, we propose to use feature pyramid instead of image pyramid. To construct such a pyramid, we introduce to use a NAC module that encodes a convolutional feature map into different scales. A unified decoding head is then applied on it to obtain object segments. Through using such feature pyramid, redundant computation can be saved, and we can do one-pass inference for all segments. Secondly, we did a systematic study of the choices for such NAC modules. We verified choices over non-parametric NACs, such as max pooling and average pooling, as well as parametric NACs, such as feed-forward network and the residual network. As shown in the table below, we can see that residual network outperforms all ablations by a large margin. Finally, we propose to learn a decoding head with regional attention. Such a decoding algorithm is supposed to first propose a region attention, and then use it to attend the feature map inside the local window, and finally decode object segments using such attended feature. Through this, our segmentation decoding procedure becomes more robust to the background noises, and the quality of foreground objects improved significantly. Here is a typical example of our learned attention. We can see that with the help of this regional attention, our framework is able to distinguish the centered foreground object from the background noises very well. As you can see, in the left example, the attention indicates the skateboard is more likely to be the target object, while in the right example, as the window shifts, our learned decoding algorithm pays attention to the human instead of the skateboard, as in the left example, for the target object. Our experimental results show that our proposed algorithm outperforms all ablation methods in terms of average recall, with at least 2 times faster speed. Note that the improvement of bounding box proposal quality is very significant. Furthermore, with a slight trade-off between speed and accuracy, our algorithm can run at almost real time. Our code is available online, and I didn't include in this poster, but please come to our poster session for details. Thank you very much.